Hi, Chris Good here with another t-test solution, and this is for if you were in the group that had question number 3. This is about the electrical stimulation of the lateral habenula. This is a brain region that we suspect may be involved in appetite regulation and food intake, and they suspect that stimulating it will decrease food intake, and they're feeding these chocolate chips to rats, and so what happens is rats have the surgery where they implant an electrode in the right side, the right habenula, and they recover for 10 days. They're kept at 80% body weight. That just means that they're healthy but they're hungry. And they're tested for the number of chocolate chips consumed during a 10-minute period of time with and without electrical stimulation. So the testing conditions are counterbalanced. Because you are testing within the same individual rat, right, this is a repeated measures study, and it's appropriately counterbalanced, so we know that there's not going to be any problem with order effects and things like that. Compute the appropriate t-test for the data presented below. So we're going to do all the steps necessary for a t-test. Number 1 being state the null hypothesis. That null hypothesis in this case is that there's a population mean difference score for all rats being stimulated and unstimulated, and that population mean difference score is going to be equal to 0, right? The treatment, the stimulation has no effect, and so the average difference in the population in terms of chocolate chips being eaten with and without stimulation is 0. Alright, number 2 is determine alpha, which for all these problems we're using alpha 0.05, and find the critical region. So we need degrees of freedom. We have 10 rats. We have 20 scores altogether, but it's the number of different scores that determine the degrees of freedom. So that number of different scores, right, minus 1, are what our degrees of freedom are. We have 10 different scores, minus 1 is 9. So the critical value for T with 9 degrees of freedom and a two-tailed test and an alpha of 0.05. Well, let's cooperate. Alpha of 0.05, degrees of freedom 9. For a two-tailed test is 2.262. Alright, so it's two tails, so it's plus and minus 2.262. And step number 3 is to calculate that statistic. T-test for repeated measures is your mean difference score minus your hypothetical population mean difference score divided by the estimated standard error of the mean difference score. Let's do the mean difference score first, just so we'll have it. The mean difference score is equal to the sum of the different scores over the number of different scores. And let's sum these up right here. I've already calculated the difference score. 12 minus 8 is 4, 7 minus 7 is 0, etc., all the way down. And we'll just add these up. 4 minus 1 minus 3, 4 minus 1 minus 3, plus 2 minus 2, plus 2, plus 2, plus 4, plus 2 is equal to 10. Alright, so the sum of all the different scores is 10. And the mean difference score, right, is 10 divided by 10, or 1. So the mean difference score is 1. Just going to double check that math once more. 4 minus 1 minus 3 plus 2 minus 2 plus 2 plus 2 plus 4 plus 2 is 10. Yeah. So the average difference score is positive 1. So we've got this part. Now we need to do the estimated standard error of the mean difference score, which is equal to the square root of the variance of the different scores divided by the number of different scores. Well, that variance, right, is equal to the sum of the squared deviations of each different score from their mean, right, divided by the degrees of freedom. That sum of squares is going to be equal to the sum of the squared difference scores minus the square of the sum of the different scores divided by the number of different scores. Let's go ahead and square these differences here. Alright, so 4 squared is 16, 0 squared is 0, then I've got 1, 9, 4, 4, 4, 4, 16, and 4. The sum of the different scores then is 16, right, plus 1 plus 9 plus 4, there's a lot of 4 here, is plus 4, plus 4, plus 4, plus 16 plus 4, 62. Alright. So, the sum of the different scores is 62. Sorry, the sum of the squared different scores. The sum of the different scores is 10. So I'm going to square that and divide by the number of different scores, which is also 10. So 10 squared is 100, divided by 10 is 10. 62 minus 10 equals 52. We'll plug this in up here. So 52 divided by the degrees of freedom, which is 9, is equal to 5.78. We'll plug this in up here, right? So the square root, 5.78, over the number of different scores. So 5.78 divided by 10 is equal to 0.58 with rounding. And the square root of that is, 0.76. Alright. So now we can plug up in here, the mean difference score was 1. The population mean difference score, we hypothesized to be 0. That was our null hypothesis. And we divide that all by 0.76 with rounding. 1 divided by 0.76 is 1.32. Okay, that's our observed value for t. Our critical value was here. I want to go ahead and draw that t distribution, shade in my critical region. So we had minus 2.262 plus 2.262, right? And we're going to shade that in. That actually goes down that way. All right, shade that critical region. The mean of t is always 0. My calculated value for t then, 1.32, is right here, not in the shaded region. Therefore, our decision, step 4, is fail to reject. Fail to reject. Let's talk about what that might mean. Well, we didn't prove that stimulating the lateral habenula does nothing. All we can really say is that we found no significant difference in the stimulated condition versus the not stimulation condition. I like to talk about what the results mean about the effect of the treatment. So we can say that stimulation of the right lateral habenula does not significantly increase eating behavior. Actually, you know what? It doesn't decrease it either. So we're going to say it does not significantly alter eating behavior in rats. I'm not done with the sentence. I'm making a comma there so I can put in my t information. So the t we calculated with 9 degrees of freedom was 1.3. I have to peek again, 2. And the p-value that's associated with that, we don't know what the proportion is beyond 1.32, right? Or beyond negative 1.32. We can't say exactly. We do know that it's less than alpha, right? Because to get a value this big or greater, or this big or smaller, these two together, that proportion is 0.05. So we know that it's greater than 0.05, right? Because it's a larger region than the critical region. beyond our calculated value of 1.32. There, that's the end of my sentence, and that's the end of the answer.